Hello, and welcome to the Nocturnal Astronomer. I'm your host, Atlas Reid, and tonight we're exploring one of the most ambitious delivery operations ever conceived. We're going to examine the physics behind Santa's Christmas Eve journey, calculating the actual requirements for visiting hundreds of millions of homes in a single night. We'll look at the speeds involved, the forces at play, and the sheer magnitude of energy required to pull off what might be the universe's most impressive feat of logistics and physics. If you enjoy these types of videos, please give this one a thumbs up and subscribe to the channel. I'd also love to know where you're watching from and what time it is there. Drop a comment below and let me know if you're listening from your bed at midnight or perhaps during a quiet afternoon. Let's dive in. To understand the physics of Santa's sleigh, we first need to establish the scope of the task. According to demographic data, there are approximately 2 billion children in the world. Not all celebrate Christmas, so we can reasonably estimate around 500 million households that Santa would need to visit. This figure accounts for multiple children per household and focuses on those homes where Christmas is celebrated with the expectation of Santa's arrival. Christmas Eve spans 31 hours when accounting for different time zones around the globe. Santa has the advantage of traveling from east to west, following the rotation of Earth and effectively extending his working window. He begins his journey at the international dateline and moves westward, gaining time as he goes. This gives him slightly more than a single rotation of Earth to complete his deliveries, but even with this advantage, the numbers become staggering. With 500 million stops to make in 31 hours, Santa has approximately 224 microseconds per household. That's less than a quarter of a millisecond at each location. During this time, he must land the sleigh, navigate to the appropriate entry point, deliver presents, consume any cookies and milk left out, and return to the sleigh before launching to the next destination. The precision required is extraordinary, operating on timescales usually reserved for electronics and high-speed photography. The distance traveled is equally impressive. Houses are not conveniently clustered together. Even with optimal routing, which itself would require computational power exceeding our most advanced supercomputers, the average distance between households would be substantial. If we conservatively estimate an average distance of 1 mile between stops, Santa would travel 500 million miles in a single night. For reference, that's more than 5 times the distance from Earth to the Sun. Now we can calculate the required velocity. 500 million miles divided by 31 hours gives us an average speed of approximately 16 million miles per hour. To put this in perspective, the speed of light is 670 million miles per hour. Santa would need to travel at roughly 2.4% the speed of light to maintain this schedule. That's approximately 21,000 times faster than the speed of sound at sea level. This velocity places Santa's sleigh firmly in the realm of relativistic physics. At 2.4% light speed, special relativity begins to have measurable effects. Time dilation would occur, meaning time would pass slightly slower for Santa than for stationary observers on Earth. The Lorentz factor at this speed is approximately 1.0003, meaning for every second that passes for Santa, about 1.0003 seconds pass on Earth. While this seems negligible, it's a real effect predicted by Einstein's theory and confirmed countless times through experiment. Moving at 16 million miles per hour through Earth's atmosphere creates problems that make re-entry of spacecraft look gentle by comparison. When the space shuttle re-entered the atmosphere, it traveled at approximately 17,000 miles per hour and generated enough heat to require specialized ceramic tiles for protection. Santa's sleigh would be moving nearly 1,000 times faster, and the physics of atmospheric heating scale roughly with the square of velocity. Air resistance, or drag, occurs because an object must push air molecules out of its path. At normal speeds, air has time to flow smoothly around objects. At supersonic speeds, air cannot move out of the way fast enough and compresses in front of the vehicle, creating shock waves. At hypersonic speeds, the compression becomes so severe that the air molecules themselves break apart. At Santa's required velocity, we enter a regime that no human engineering has ever approached in atmosphere. The kinetic energy of the air molecules being struck by the sleigh would be immense. When we calculate the energy transfer, we find that each cubic meter of air the sleigh passes through would receive energy equivalent to a substantial explosive blast. This energy converts almost entirely to heat. The front surface of the sleigh would experience temperatures far exceeding those found on the surface of the sun, which sits around 10,000 degrees Fahrenheit. We would be looking at temperatures in the millions of degrees. At such temperatures, matter exists only as plasma, where electrons are stripped from atoms. The sleigh would create a continuous explosion along its path, leaving a trail of superheated plasma stretching around the globe. The sonic boom would not be a boom at all, but rather a continuous roar of devastating pressure waves. The energy released would be visible from space as a brilliant streak of light circling the planet. The thermal radiation alone would be catastrophic. Objects heated to millions of degrees emit intense radiation across the electromagnetic spectrum, from radio waves through visible light and into hard X-rays. This radiation would propagate outward from the sleigh's path, potentially causing widespread damage to anything nearby. The infrared radiation would be sufficient to ignite flammable materials at considerable distances from the flight path. Let's consider the reindeer for a moment. At the front of this formation, Rudolph's famous red nose would face the full force of atmospheric compression. Even if we imagine the nose as some form of exotic matter capable of withstanding these conditions, the energy it would need to dissipate is beyond calculation with conventional physics. The glow would not be a gentle red, but rather a blinding white typical of objects heated beyond the temperature of any conventional material. The sleigh itself would need to be constructed from materials that do not exist in any laboratory on Earth. Even tungsten, which has the highest melting point of any element at 6,192 degrees Fahrenheit, would vaporize instantly. Carbon in its diamond form, the hardest natural material, would transform to gas. We would need to invoke materials from theoretical physics, perhaps strange matter or other exotic states that might exist in neutron stars. The challenge of maintaining 16 million miles per hour is one thing, but stopping and starting 500 million times adds another layer of impossible physics. At each household, Santa must decelerate from this tremendous velocity to a complete stop, then accelerate back to full speed to reach the next destination. The forces involved would be truly extraordinary. Acceleration is measured in G's, where 1 g equals the acceleration due to Earth's gravity, about 32 feet per second squared. Humans can tolerate around 5 Gs for extended periods with proper equipment and training. Fighter pilots may experience 9 Gs during tight maneuvers. Above 15 Gs, most people lose consciousness as blood is forced away from the brain. At 50 Gs, fatal injuries occur even with the best protective equipment. Let's calculate the acceleration required. If Santa takes even 1/10 of his available time at each stop for the deceleration and acceleration phases, that's approximately 22 microseconds for each process. Starting from 16 million miles per hour, or about 23 million feet per second, and coming to a complete stop in 22 microseconds requires truly staggering deceleration. The mathematics yields an average deceleration of approximately 1 trillion feet per second squared. Converting to Gs, this represents about 30 billion Gs. To put this in perspective, this is roughly the acceleration experienced by particles in the largest particle accelerators, where protons are brought to near light speed. No biological material could withstand even a tiny fraction of this force. At such accelerations, the molecular bonds holding matter together would fail catastrophically. The human body, or presumably the reindeer body, would not simply be compressed or injured at these accelerations. The individual atoms would experience forces far exceeding the electromagnetic forces that hold molecules together. Santa and the reindeer would be disassembled at the atomic level during each deceleration. They would then need to be reassembled perfectly before the next acceleration. This moves us well beyond conventional physics into the realm of science fiction. Even if we could somehow protect the passengers from these forces, the sleigh itself presents problems. The structural integrity of any material is limited by the strength of chemical bonds. Steel, one of our strongest common materials, has a tensile strength of about 80,000 pounds per square inch. At 30 billion Gs, even a small mass experiences forces that would shear through steel like tissue paper. The entire sleigh would need to have zero mass or be constructed from something held together by forces stronger than electromagnetic, perhaps involving the strong nuclear force that binds atomic nuclei. The energy required for these accelerations is equally staggering. Kinetic energy equals 1/2 mass times velocity squared. Each time Santa accelerates back to full speed, the sleigh gains an enormous amount of kinetic energy. This energy must come from somewhere. If we assume a modest sleigh mass of 1,000 pounds, including Santa, reindeer, and presents, each acceleration to 16 million miles per hour requires about 90 trillion joules of energy. That's equivalent to about 22 kilotons of TNT, roughly the yield of the atomic bomb dropped on Nagasaki. Santa would need to release this much energy 500 million times in one night. Beyond the sleigh itself, we must consider what Santa is carrying. The whole purpose of this journey is to deliver presents, and the physics of the payload creates its own set of impossible challenges. Let's be conservative and assume each child receives one present weighing an average of 2 pounds. With 500 million households averaging 2.5 children each, that's 1.25 billion presents. 2 pounds per present multiplied by 1.25 billion presents gives us 2.5 billion pounds of cargo, or 1.25 million tons. This is comparable to the weight of a large aircraft carrier or a small mountain. The sleigh would essentially be hauling a chunk of solid rock around the world at 2.4% of light speed. The structural requirements to keep this cargo together under the acceleration forces we discussed would be impossible with any known engineering. But the presents themselves pose additional problems. At each stop, Santa must select the correct presents for that particular household from his cargo hold. In 224 microseconds, he needs to locate, retrieve, and deliver the appropriate items. If we imagine the presents organized in the most efficient possible system, Santa would still need to move at superhuman speeds just to sort through the inventory. His hands would need to move faster than any robotic system we've ever created, selecting and transporting items with perfect accuracy. The volume of presents creates practical problems too. 2 pounds might be a small toy or book, with an average volume of perhaps half a cubic foot. 1.25 billion presents would occupy over 600 million cubic feet, or about 15 million cubic meters. This is roughly equivalent to a cube measuring 800 feet on each side. The Sleigh would need to be enormous, essentially a flying warehouse. The aerodynamics of such a structure, even setting aside the impossible speed requirements, would be challenging. As presents are delivered throughout the night, the mass of the Sleigh decreases continuously. This changes the dynamics of flight considerably. With each stop, the Sleigh becomes lighter, requiring less energy to accelerate but also becoming more responsive to forces. The flight control system would need to constantly adjust for the changing mass distribution. By the end of the night, the Sleigh would be empty, massing perhaps 10,000 pounds compared to the initial 2.5 billion pounds. This represents a mass ratio of 250,000 to 1, far exceeding anything in conventional aerospace engineering. The presents themselves must survive the journey. At 30 billion Gs, anything not rigidly attached to the Sleigh structure would be crushed into its backing surface with incredible force. Delicate items like electronics, dolls, or toys would be pulverized into dust by the acceleration forces. Even solid blocks of metal would deform under such stress. Every present would need to be individually protected by some form of inertial dampening system, technology that exists only in science fiction. There's also the question of wrapping paper. Traditional gift wrap would be shredded instantly by the aerodynamic forces at 16 million miles per hour. Even at conventional aircraft speeds, loose materials are torn away by airflow. At hypersonic velocities, the wrapping paper would be vaporized by aerodynamic heating before it could even tear. Each present would need to be encased in the same exotic materials as the Sleigh itself, defeating the cheerful aesthetic of colorfully wrapped gifts. The computational requirements for Santa's journey rival the physical impossibilities. Plotting an optimal route through 500 million stops is a variation of the traveling salesman problem, one of the most famous computational challenges in mathematics. For even a few dozen stops, finding the absolute shortest route requires checking every possible combination. The number of possible routes through 500 million locations is a number so large it defies comprehension. To put this in perspective, if we had a computer capable of evaluating 1 trillion routes per second, and we started that computer at the beginning of the universe 13.8 billion years ago, we would have evaluated only an infinitesimally tiny fraction of the possible routes by now. The number of permutations of 500 million items is approximately 10 to the power of 1 billion, a number with over a billion digits. Even writing this number down would require more atoms than exist in the observable universe. Instead of finding the perfect route, we might settle for a good route using approximation algorithms. Modern logistics companies use sophisticated software to optimize delivery routes, finding solutions that are close to optimal even if not perfect. However, even these algorithms struggle with problems of this magnitude. The best current approaches might handle tens of thousands of locations effectively. Scaling to 500 million would require computational advances we cannot currently imagine. The navigation itself operates on timescales that challenge human comprehension. At 16 million miles per hour, the Sleigh travels about 4.4 miles per millisecond. The time between stops averages 224 microseconds, during which the Sleigh must know its exact position, orientation, and velocity, adjust course toward the next destination, and prepare for deceleration. This requires position updates and course corrections on the order of microseconds, far faster than any navigation system currently in existence. GPS satellites, which provide positioning accurate to within a few meters, update at rates measured in seconds. Aircraft navigation systems might update several times per second. The Sleigh would need updates millions of times per second, with accuracy measured in inches rather than meters. At these speeds, even small errors would be catastrophic. Being off target by 1 degree at 16 million miles per hour would result in missing the destination by hundreds of miles. The Sleigh must also track the rotation of Earth. Our planet rotates at about 1,000 miles per hour at the equator, which is significant when crossing time zones. The Sleigh's navigation computer must account for this rotation, ensuring that Christmas Eve remains Christmas Eve throughout the journey. This requires precise timekeeping synchronized across all time zones, essentially implementing a global coordinate system accurate to microseconds. Weather presents additional navigation challenges. Wind patterns, storms, and atmospheric conditions vary constantly across the globe. At conventional aircraft speeds, pilots can often navigate around bad weather. At 16 million miles per hour, there is no time to maneuver around obstacles. The Sleigh would need to either punch through weather systems, experiencing forces from wind and precipitation, or fly at altitudes above weather patterns. However, as we discussed with atmospheric heating, being in atmosphere at all creates insurmountable problems at these velocities. We've touched on energy needs during acceleration, but let's examine the total energy budget for the entire journey. This calculation reveals perhaps the most staggering aspect of Santa's operation. Energy requirements fall into several categories, including kinetic energy for movement, heat dissipation, and the work done against atmospheric resistance. Each represents an impossible demand on any conceivable power source. The kinetic energy of the Sleigh at full speed, assuming our conservative 1,000-pound empty mass, is about 90 trillion joules. However, this energy must be supplied 500 million times as Santa accelerates at each stop. The total energy for acceleration alone would be about 45 quintillion joules. 1 quintillion is a billion, a number so large it's difficult to grasp. This is equivalent to about 11 billion tons of TNT, or roughly 700,000 times the yield of the largest nuclear weapon ever detonated. But acceleration energy is only part of the story. The primary energy drain comes from fighting atmospheric resistance. Every second, the Sleigh must push through air, imparting tremendous energy to the atmosphere. The drag force on an object moving through air is proportional to air density, frontal area, and the square of velocity. At 16 million miles per hour, even with an aerodynamically optimized shape, the drag force would be colossal. A rough calculation suggests the Sleigh would experience drag forces measured in trillions of pounds. The power required to overcome this drag equals force times velocity, yielding power requirements in the range of 10 to the 20 watts, or 100 quintillion watts. For comparison, total human energy consumption across all sources is about 20 trillion watts. The Sleigh would require power equal to 5 million times all of human civilization's energy use, sustained continuously for 31 hours. Where could such power come from? Let's consider various energy sources. Chemical energy, like burning gasoline or rocket fuel, stores about 40 million joules per kilogram. To supply 45 quintillion joules would require over 1 billion tons of fuel, comparable to the entire cargo weight we calculated earlier. This fuel would need to be carried along, increasing the mass and therefore the energy requirements further. Chemical energy is clearly insufficient. Nuclear energy offers more power per unit mass. The fission of 1 kilogram of uranium releases about 80 trillion joules. The fusion of 1 kilogram of hydrogen into helium releases about 600 trillion joules. Even fusion, the most energetic conventional nuclear process, would require tens of millions of kilograms of fuel. While While more feasible than chemical energy, the required reactor to convert this fuel to usable power at the necessary rate would be enormous, likely massing more than the fuel itself. Perhaps antimatter could work. When matter and antimatter annihilate, they convert mass to energy according to Einstein's equation E equals mc squared. 1 kilogram of matter combining with 1 kilogram of antimatter releases 9 times 10 to the 16th joules, or 90 quadrillion joules. This means about 500 kilograms each of matter and antimatter would suffice for the energy requirements. However, antimatter doesn't exist naturally on Earth, and producing it requires more energy than it releases. Also, storing antimatter safely remains a challenge, as contact with normal matter causes instant annihilation. The most speculative option would be zero-point energy, a concept from quantum mechanics. Quantum field theory suggests that even empty space contains energy due to quantum fluctuations. Some interpretations suggest this energy density might be enormous. However, extracting zero-point energy remains purely theoretical. No experimental evidence suggests we can tap this energy source, and many physicists question whether it can be extracted at all without violating thermodynamics. At 2.4% of light speed, we cannot ignore special relativity. Einstein's theory fundamentally changes how we understand space, time, and motion at high velocities. While the effects at this speed are subtle compared to speeds approaching light speed, they're measurable and have real consequences for Santa's journey. Understanding these effects requires diving into some of the most beautiful and counterintuitive physics ever discovered. Time dilation is perhaps the most famous relativistic effect. Moving clocks run slower than stationary ones, an effect proven countless times in experiments. The factor by which time slows is given by the Lorentz factor, gamma, calculated as 1 divided by the square root of 1 minus v squared over c squared, where v is velocity and c is light speed. For Santa at 0.024 times c, gamma is approximately 1.0003. This means for every second that passes on the sleigh, about 1.0003 seconds pass on Earth. Over the 31-hour journey, Santa would experience about 31 hours while Earth experiences about 31.093 hours. Santa would age about 5.5 minutes less than people on Earth during his journey. While small, this is a real effect. Santa effectively travels slightly into Earth's future, though only by minutes. Length contraction is another relativistic effect. Objects appear shortened along their direction of motion to stationary observers. The sleigh, measured by someone on the ground, would appear about 0.03% shorter in its direction of travel than its actual length measured in the sleigh's own reference frame. For a sleigh 20 feet long, this contraction would be less than 1/10 of an inch, barely noticeable but theoretically present. Mass increase is a third relativistic effect, though it's more accurate to say that momentum increases faster than Newtonian physics would predict. As objects approach light speed, accelerating them further requires increasingly more energy. At 2.4% light speed, this effect is again small. The relativistic momentum is only about 0.3% higher than the classical Newtonian prediction. However, at the extreme accelerations required, even small effects could be significant. The Doppler effect becomes extreme at relativistic speeds. Light from sources the sleigh is approaching would be shifted toward higher frequencies. Light from sources the sleigh is moving away from would be redshifted. At 16 million miles per hour, visible light from houses ahead would shift into the ultraviolet, while light from houses behind would shift toward infrared. Santa would need special vision systems to see anything in normal colors. More intriguingly, the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, would appear dramatically different to Santa. In the direction of motion, this normally microwave radiation would be blue shifted into visible light and beyond. Behind the sleigh, it would shift to even longer wavelengths. The sleigh would be bathed in a forward glow of radiation simply from its motion through the universe's background radiation. Interestingly, if Santa could somehow accelerate to much higher speeds, approaching light speed, time dilation would become more pronounced. At 90% light speed, the Lorentz factor is about 2.3, meaning Santa would experience less than half the passage of time compared to Earth. At 99.9% light speed, 1 year on the sleigh would equal about 22 years on Earth. If physics permitted extreme speeds, Santa could potentially deliver presents across centuries of Earth time while experiencing only a single night himself. However, the energy requirements scale dramatically with speed, making even higher velocities even more impossible than the already impossible speeds we've been discussing. Given the overwhelming physical impossibilities we've explored, perhaps we should consider alternative explanations for how Santa might accomplish his task. These alternatives range from the almost plausible to the wildly speculative, invoking advanced physics, alternate dimensions, and concepts at the boundaries of human understanding. While none escape the fundamental problems we've identified, they offer interesting thought experiments. One possibility is quantum tunneling on a macroscopic scale. In quantum mechanics, particles can occasionally pass through barriers they classically shouldn't be able to penetrate. An electron might tunnel through an energy barrier that should be insurmountable. This occurs because quantum particles exist as probability waves, with a small probability of being found on the other side of barriers. If this could somehow scale to macroscopic systems, Santa might tunnel through space itself, appearing at destinations without crossing the intervening distance. Another speculative approach involves wormholes, theoretical shortcuts through space-time. Einstein's general relativity permits solutions where space-time curves back on itself, creating tunnels connecting distant points. If Santa could generate and traverse wormholes, he might step from one location to another instantaneously. However, known physics suggests wormholes, if they exist, would require exotic matter with negative energy density to remain stable. Creating and controlling wormholes remains firmly in science fiction territory. Perhaps Santa operates in multiple dimensions beyond our familiar three spatial dimensions. String theory and related approaches in theoretical physics suggest reality might contain additional dimensions, compacted or hidden from normal perception. If Santa could access these dimensions, he might travel vast distances through conventional space by taking small steps through higher dimensions. This is analogous to how a two-dimensional creature living on the surface of a sphere could take shortcuts through the three-dimensional space the sphere exists in. Quantum entanglement offers another exotic possibility. When particles become entangled, measuring one instantly affects the other, regardless of distance. Einstein called this spooky action at a distance. While entanglement doesn't allow information or matter to be transmitted faster than light in conventional ways, perhaps sufficiently advanced technology could exploit quantum effects we don't yet understand. Santa might maintain quantum connections with all destination households, allowing instantaneous presence at multiple locations. Time travel presents perhaps the most intriguing option. If Santa could manipulate time itself, he wouldn't need impossible speeds. He could visit each household with hours to spare, experiencing days or weeks of subjective time while only a single night passes on Earth. General relativity permits solutions involving closed time-like curves, where time loops back on itself. Near-rotating black holes, for instance, paths through space-time might circle back to earlier times. However, time travel raises infamous paradoxes and causality problems that physicists still grapple with. A more mundane explanation might be that Santa employs an army of helpers, distributing the workload across millions of individuals. Instead of one sleigh making 500 million stops, millions of sleighs each make hundreds of stops. This reduces the speed requirements dramatically. At these reduced speeds, one could imagine advanced but not impossible technology handling the task. Of course, this interpretation moves away from the traditional single Santa narrative, but it's by far the most physically plausible approach. And on that note, we've explored the truly staggering physics challenges that Santa's Christmas Eve journey would entail. We've seen that maintaining the necessary speed would require energy exceeding our entire civilization's output, that atmospheric heating would create temperatures rivaling stellar cores, that acceleration forces would disassemble matter at the atomic level, and that the computational and logistical demands defy the fastest computers imaginable. Every approach we've taken leads to impossibilities stacked upon impossibilities. Yet perhaps that's exactly the point. The magic of the Santa story lies precisely in its impossibility. It represents our desire to believe that some things transcend physics, that wonder and joy operate on principles beyond scientific analysis. The mathematics and physics we've explored tonight highlight not the failure of the story, but rather the gulf between cold physical law and the warmth of human imagination. Sometimes the most important truths aren't found in equations. Thank you for joining me on this journey through the physics of the impossible. Whether you're drifting off to sleep or simply pondering the universe, I hope you've found these calculations fascinating. Until next time, keep looking up at the stars and wondering what might be possible just beyond the edge of our current understanding. This is Atlas Reid with the Nocturnal Astronomer, wishing you clear skies and curious dreams.